Thanks, everybody. What a lovely venue we have here today. Although the downside of being the morning keynote is I can't walk up with a glass of wine. It's probably a little bit inappropriate. So I'm going to talk a little today about incident response at planetary scale. And one of the challenges that an organization like Akamai has in managing incidents and understanding what's going on. And I always love looking at incidents through a number of different lenses. And so the first question is, what really is an incident? And so here's sort of an alert one might see. It says, 25% of the machines are operating over nominal maximum CPU load, whatever your max might be. This is the sort of alert you might write to fire. And the really important thing here is, what's the actual incident? What's the first question that you want to ask? If you're the responder who first sees the alert or the subject matter expert who first gets called. And historically, in the days before we had telemetry-based monitoring systems, everybody would focus on those 25%. What's wrong with these machines? Which application has run amok? And I posit that's actually the wrong first question. It's a great second question. But the first question is, well, what about the other 75% of my machines? And in traditional logging-based alerting systems, you have no information about that. You have to go manually hunt that down, rather than being able to ask the question, well, show me the histogram of CPU load across all of my network, so I know whether I have a meltdown about to happen, that 25% have crossed this threshold, or whether I have a load balancing problem because 75% of my network is currently doing nothing. And so that's the basis of a challenge that we have. So here's a little bit about Akamai. So we have about 250,000 servers scattered in 1,500 different networks. Some of you are here today. Many of you aren't. In 136 countries. Do not have humans where those servers are. All interaction has to be done remotely from one of our 4 operation sites, 2 here in the US, 1 in Poland, 1 in India. Now, when we look at sort of what Akamai does, if you're not familiar with us, historically we're a content delivery network. We represent the edge, delivering websites for many of your organizations, other organizations. We pivoted over the last 10 years to being more of a security company. We're doing DDoS protection, WAF, mitigation, bot management. And all of that is running on our same telemetry-based system for reporting information about what's going on. So attackers get to attack us probably more often than anybody else. So that's a regular problem we deal with. Our recent traffic peak was about 100 terabits per second, a little over that. And so we're trying to capture information and telemetry about a network that is routinely seeing close to 100 million requests per second. And so we have to collect data and aggregate and understand what's going on there. One of my jobs is overseeing incident management. And for Akamai, an incident is not a security incident. It is any incident that is going to impact the performance of our networks. All of that is governed by my organization. We have a distributed system for actually operating those incidents. But it's helpful to understand sort of what is an incident. So an incident is any place that we enter into an unacceptable loss. Right? We lose one server, that's totally acceptable. We expect that to happen. Anywhere between 1% and 5% of our servers are unavailable at any given time for service. So clearly that's not an incident. But not being able to serve one of our customers, their website goes down, that's an unacceptable loss. So when we think about incidents, we have to understand what hazards might put those incidents in play. So what are the environmental hazards? And I'm not referring just to Mother Nature. Although I will admit we have a number of incidents that get caused by natural disasters. But many of them are the hazards we ourselves might put in. Did we have insufficient safeties on making a software change? Did we have a feature that there exists, one of our worst things we call the request of death, which is where a customer configuration combined with our software, combined with a specific request a user might make, can kill a server. Right? That's an environmental hazard. If we're in that state, the request is just the trigger. And so how do we understand those hazards? And then what controls can we put in place to either prevent them or detect them so that we can better mitigate them? And that's really how we're structured from an incident management. Here's how we think about incidents from a response life cycle. So I want to talk about sort of how we respond. There's the world that everybody thinks they're in, which is safe. right? Let's be honest, nobody's ever actually in the safe state, but that's a very common belief that engineering management will have, or certainly business management. You move through known hazards to controlled hazards. Well, there's a risk, but I've got some controls around it, to a state of uncontrolled hazard and into a state of loss. And what's helpful about using language from the safety world, even in the security incident space, is that it lets you change the dynamic about a conversation about incidents. Because people often want to say, like, is this secure? It's one of my favorite questions we often get is this secure? And it reminds me of a joke that Caspar Weinberger, the former Secretary of Defense of the United States, once said that the hardest part of his job is talking, because the English language confuses the military. If he gave an order to go secure a building, so using that magic word secure, and he told the Marines, any Marines in the room? Wow, no. Okay, told the Marines to secure the building, they'll kill everybody inside and blow up the building for good measure. Usually the Marines all cheer when you tell that one. If you tell the Army to go secure a building, they'll put up sandbags around it and some concertina wire, and they'll have checkpoints with a password of the day. Sounds actually very familiar to the security industry. If you ask the Navy to secure a building, they will turn off all the lights and close the windows and lock the doors on the way out. And if you ask the Air Force to secure a building, we would get you a 3-year lease with an option to buy. So secure is a dangerous word. Safe is also a dangerous word, but far fewer people have experience with that word and how ambiguous it can be. So we like to talk about losses. And the way that an incident operates is you often are in some normal operational state, and at some point, some risk changes. And you start to be in a dangerous world where you no longer have control of your hazards. And you rarely know when you're in that world. And then at some point, some trigger happens and you encounter a loss, and now you know you're in that world, and we start incident response. This is often where incidents will start in phase 1, where minutes matter. You just have to fix the bleed, get to a world where now you can recover. But first, stop the loss. Then as you mitigate back, you have phase 2, phase 3 of your incidents, as you begin to regain control of your network and develop a long-term sustainable mitigation. And hopefully you get to phase 4, where you can learn about what went wrong. Now, what's missing from here is my favorite phase of incidents, which is phase 0, which is where you can detect that you're about to hit a loss state and potentially mitigate the incident before the loss. And this is where telemetry-based systems are amazingly helpful. Because if you can say, well, I'm in an incident if 25% of my network isn't behaving well give me an alert at 15%, so that maybe I can start to operate before I get to that. Maybe give me a threshold when I'm at 80% of nominal load for those machines, rather than 95% of nominal load. The danger of phase 0 operations is that if you manage to successfully mitigate the incident, people will often ask, well, why did you bother declaring an incident if you never had a loss? So be careful if you deal with any resultists who judge a process by the outcomes rather than by the choices that were correctly made during the process. Incident severities are important. In the security world, we often use weird names for incidents and their severities. We have found it very helpful to only have one set of severities for all incidents, whether it's a security incident, a performance incident, a cost incident. If we spend more money than we thought we were going to spend, that's an incident. And so we have 4 incidents, severities, but it turns out 4 is really a dangerous number to give humans because they're really only good with 3 different choices. So we sort of bucket these, and we say, well, if it impacted a customer, then 1 and 2 is sort of the same. And if I have any customers in here, I'll be very honest. The reason for this is that whatever I do to one customer can never be a severity 1 incident, right? I have thousands of customers. I have to hurt multiple of them for it to be a severity 1 incident. But I want to use the same tools if I have badly hurt 1 customer or badly hurt 50. Whereas if I have an internal incident that's not impacting customers, I want to not necessarily use those same tools. We often think about these tools as if they are credit cards. Right? If I have a severity 4 incident, it's minor. You just have your normal Amex Gold card to go spend on solving this incident. If it gets up to that severity 3 for customers or severity 2 or 3 for internal, now I'm going to pull out the platinum card. And of course, if it gets up into that severity 1, that dangerous place, I'm going to pull out the cobalt card. And now what's interesting here is that you should understand when you're investigating an incident, if you have the common severities, then if you're talking about a security incident to people who are not in the security world, all they have to hear is severity 1, and they understand exactly what powers you have given to the incident team. Right? We're not talking about, oh, we have a small data compromise off in some place. They want to know how bad it is. You get to say severity 1. For us, that's really important as we deal across multiple business units to have a common language that is just about the scores of an incident so people can understand it. Now, the thing that probably folks are really interested in, which is the Akamai Query system. Akamai Query is the great-grandfather, great-grandparent of osquery in some ways, which is this was built in 1998, has been continuously operating since then. It has derivatives in a number of different companies from Akamai engineers who left and went elsewhere, among them Facebook, who built similar systems, learned some of the lessons from ours, so are better in some ways, unlearned some of the lessons, so have made different choices in other ways. So a little highlight of how Akamai Query works and how it might be a little different than what you're used to for osquery. The heart of Akamai Query is a library called the TableProv, for table provider. It's a library that any application can include that provides an interface for asking that application to provide tables of information that's going on. So for instance, our Edge server application provides a number of tables, one of which is probably our most heavily used, called CP GeoLoad Info, which stands for Content Provider Geographic Load Information. I can ask any Edge server, and what it will give me back is a table that says, for these content provider codes, the numeric code that corresponds to some subset of a given customer, into these geographies, here's exactly how much traffic I'm currently delivering. So I can ask that. So every application has this embedded. There's an additional monitoring application that just generally monitors health of the machine, looking at things like what's happening on the disk. Then there's an application that runs called Query that is just a proxy for that information. And what Query does, if it's looking for a table, it looks up which application has it, makes a connection and says, just give me that table right now, please. Now what it will do is, as long as it wants that data, is it will continuously refresh. It will poll about every 10 seconds if it's actively looking, every minute if it's passively looking, and say, hey, just give me an update on what that data is. When it gets new data, it discards the old data and inserts it into the table. Now in an Edge machine, this is really easy because that discard and insert just looks like drop the whole table and just put in something new. But what makes Query really neat is the way the aggregation system works. So we have network aggregators. We have 42 different Akamai service networks. Each one has its own aggregators. What those aggregators do is they will reach into all of the Edge servers within that network, and they'll say, hey, I want this table from you. And every time they get an update, they find the rows that corresponded to that server from their first request, drop them out, and insert the new rows. So what we get is this really interesting view that is not necessarily synchronized across our network. So an aggregator knows something about every machine that's currently reporting, but for one machine that might be 5-second-old data, for another machine that might be 8-second-old data, and for another machine it might be instantaneous data. So there's some danger in correlating that data in real time, but there's some really powerful benefits. It gives us this near real-time view of everything that's currently going on within the network. Now, the network aggregators then report up to mega aggregators that read across the whole network. Not all of their information is going to the mega aggregators. I'll get to why in just a moment. And those mega aggregators now have tables that span the entire networks. So we can look across all of our systems to understand what's happening there. We also have an alert definition and management system that is where we write the SQL queries that are being continuously run against these systems. And when they return results, they will fire alerts into our NOC or potentially into other places. And so that's the fundamentals of the Akamai Query system, which is what we're used to do all of our real-time telemetry and most of our near real-time reporting. If you're an Akamai customer and you ever go into our portal, and you'll see for your traffic graphs, you'll see sort of two areas of it. There's this line, and the last 4 hours has a shading in it, and everything beyond that isn't shaded. The last 4 hours is all drawn off of query data. Everything that's older than that, we're drawing off logging data where we're writing a log line for every request, and then we're collecting those and providing visibility into it. So the power for this is it gives us that real-time telemetry. I can ask, what's the CPU utilization of every machine on the network? And if I really want 250,000 rows of data, I can get 250,000 rows of data in real time because that's data that we're constantly pulling into the network. So the data is large. The number of tables that we have at the edge of the network is 11,500 different tables. Now, we don't pull all of those. Here's one of the powers of the query system, which comes back to the incident response. When we have an incident, who do we call? Like, we have professional incident managers in our operations team that can run incidents, but the people that we call are the professional subject matter experts, often the engineers who built the system. They're the ones who have to do the debugging. So we incentivize them to create the tables that will give them information in an incident. And so those tables aren't all being pulled all the time. They may have to run a query. It'll take them a couple minutes for it to pull the data off of everything and give them a full table. But now they can get all of the information off of the network without writing scripts to go out and try to pull in data, without having to log into all of those machines. It makes me very happy when I can keep people from logging into machines. So only about 6,000 of those tables are actively being pulled all the way into the aggregators. So almost 50% are for debugging purposes rather than real-time operational information. The number of rows across our network aggregators, if we put them into sort of one location, would be 17 billion rows of data. What the mega aggregators see is a subset of that, so they're only seeing about 5.2 billion rows of data. So in real time, that's what we have access to about the health and safety of our network at all times. The memory footprint is substantial. The total set of network aggregators need about 605 gigabits to collect all of that data into one place, which is why we have network aggregators, so we don't have to collect it in one spot. But the mega aggregators use 182 gig of RAM to be able to look at that data. So that's a large challenge, and probably the single biggest challenge we have in operating our aggregator network is keeping that memory pressure manageable, is understanding what data should be there, because that's a substantial cost. We have about 900 of those 250,000 machines in our network are just aggregators, just to collect all of this information so that we can run our alerting system. The number of queries we have defined in our alert management system is 46,000, 8,000 of which are what we call operational queries. An operational query is one which, if it returns results, fires an alert into our NOC. The rest of these are all queries that are being run by developers. Maybe a developer wants to understand how their system's operating, so they program a query to run once a day that will tell them some information at a peak time, or once an hour, and it's going to collect data. We have ancillary non-operational systems that will collect the data off of this, shove it into RRD databases so that we can get trend lines out of it. Right? The query system that we have here is only a real-time view. It doesn't have any history. The history is all aggregated off of some of these secondary queries. Now, what that means is that we're running about 12.7 million queries a day is being run in an automated fashion. 8 million of those are queries that, if they return results, are going to fire alerts into our NOC. Now, some important things about those 8 million queries that are running to fire alerts into our NOC, many of those will not fire alerts into the NOC the first time they return a row. Right, one thing we've learned to look for is blips, things that are not actually that interesting. In the security world, blips are very fascinating, but in the operational world, they're often not. You hit a fringe event, so we can tell queries that until you return 3 rows in a row, you run for 3 cycles, you're not allowed to fire an alert. And so that logic is baked into the alert management system so that we're able to not have people panicking and dealing with issues. Most of these alerts all fire into our NOC. Anybody who's in Cambridge who wants a tour, drop by. The folks there are looking at individual alerts in the same way that we have aggregators that separate by network. We separate our humans by network. So we'll have NOC shift. A technician might be working on our secure content delivery network, so they're only going to see alerts for that rather than seeing alerts across the whole network. That really allows us to make sure people aren't doing as much context switching, that maybe alerts are correlated that a human might see that we hadn't yet written alerts for. So the big part of incident management is not the real-time incident response. right? That's always an important thing. But the real question is, what do you do about this later? How do you learn from an incident? And how do you understand what tools you should apply? Sometimes the correct answer is you stay in an incident until you solve the problem, but other times it's not. And so we like to understand, how bad is a hazard by looking at context as we're doing our incident response. And so everybody probably gets to do loss expectancy and risk probability scoring. I think it is mostly bunk, but it's a great way to communicate with managers and other humans. So we take the standard 9 box and we flip it on its side. First we ask the 2 questions: how likely could it be and how bad could it be? And likelihood, everybody's probably already saying, you can't guess at likelihood. Like, we don't actually know these numbers, they're not actuarial, which is why we use qualitative definitions. We have one definition that is things that are repeating, which is if I keep having the same incident happen over and over and over again, that is the most likely incident thing I'm going to have. We have what we call plausible, which is it has either happened once, but not again, or we can't for the life of us figure out why it hasn't happened, right? And you probably all have states like that where you're like, I have a thing that's obvious and easy for somebody to attack and nobody has yet, but I don't understand why. So we call those plausible. Then we talk about the surprisingness of an incident, and we talk about who is surprised. And it's not about whether I am mildly or very surprised. We categorize our decision makers into the gullible, the normal, and the paranoid. And we say that if you are a product manager, no offense to any product, actually lots of offense in some ways, you are highly gullible, right? And this is because product managers are people that we ask to go out and take lots of risk and to believe that their products will always succeed in the marketplace. And so they're trained to reduce risk awareness, right? And so we say, look, if they would be surprised, that's the sort of thing that is that is actually only mildly surprising if they would be surprised. Or if they wouldn't be surprised, sorry, if that's the cusp point. And then we take our engineering managers, the people we think balance risk, and say, well, the cusp point where they go from being surprised to not surprised, that's the moderately surprising. And then we take the paranoid people, mostly the folks who work for me, and say, look, if they say they wouldn't be that this was the sort of thing that they'd be surprised by, it's their cusp point, those are the very surprising. And then, of course, we take our incident severities from the earlier discussion, and now note I've added in a new severity. And this one's really important, especially if you ever want to talk to your board, is you always want to add in something a little extra, right? And the disaster severity is a really key one. And disasters are just severity 1 incidents that after which you have to change your business model, right? If you're going to come out of an incident and recognize that the way that you operated the business, you can't do that anymore. And it's not just changing a procedure or a piece of software. It's things like for us in 2009 when we were breached by the Chinese government during Operation Aurora. Right? We lost control of our corporate network. We had to clean that up. We spent 10 years changing the architecture of our corporate network to build a zero trust model when nobody else had one, because we needed to do that. For us, Operation Aurora was a disaster, right? It's a level of incident that was terrifying. And so now you can just put bubbles at each of these cross points. And then we don't try to prioritize within each one of these tiers. We just say, look, there's tier 0, which is a disaster that's going on right now. Tier 1, a Sev 1 that keeps happening, or a plausible disaster, et cetera. And what's fascinating about this is if I take almost any hazard in a business, I can give you multiple plausible scenarios for how that disaster unfolds, and almost all of them will show up in the same row. Which is to say, if I have a repeating severity 3 problem, I can almost certainly describe a plausible severity 2 problem, and a mildly surprising severity 1 problem, and a moderately surprising disaster, all out of the same hazard. And so now it gives us some tools to talk about how do we fix these things. When we look at these problems and we say, this is a tier 2 problem, and sometimes you have a hazard that's a tier 2 hazard, and all of a sudden you have an incident that looks a lot like it's tier 1. That's really interesting. Maybe we didn't understand our hazard, and maybe we need to solve it. And so what tools should we use, right? Should we use incidents? And incident response is a really effective and really expensive tool. It is the most disruptive thing that businesses can often do to themselves. Because in an incident, I have a severity 1 incident, I can redirect any engineer in the company to do whatever I think they should do. Right? That's why we only have about 20 people who get that Cobalt card, because that's the power they have. They can override engineering priorities. We can stop product launches, stop releases. So those are dangerous. You'd better have a really high benefit because you can't afford the cost for very long. It is low cost in time, not in immediate impact. So use incidents for that. The best are, of course, what we think of as routine work, change requests, where you say, look, I can get a small amount of benefit for a small amount of cost, and so I really need a small amount of overhead. I should be able to file a ticket in, put in a Jira ticket or Bugzilla or, pull request, and be able to have this work just done. Now, the dangerous and hard thing for me that I have to deal with are what we call the executive vulnerabilities. They're often called executive vulnerabilities because the single biggest hazard is the executives, because this is large work that takes a lot of time across multiple business units. And so sometimes out of an incident, you recognize that solving this problem isn't going to happen in incident tempo and cannot be done by incident managers. Right? Because incident managers are either operational staff who have other incidents to go work on, or they're engineering staff who have other projects to go work on. And so executive vulnerabilities get run out of my organization. Doesn't matter where they come out of, they end up with us, and we'll prioritize a small number of them because they're highly disruptive. And then there's the things you have to live with. And recognize this. When doing incident management, there are hazards you just suck up. That you say, this is a problem, and we're going to live with this problem, and you'll be very open and upfront about the problem. There's a tendency that people have to want to say the problem doesn't exist, because that's much more palatable than saying, well, it's one that we just have to live with. So my recommendation for anybody who finds themselves in that is come up with the vulnerability of the hazard that everybody really accepts. Of course, we're not going to do anything about that. For us, our headquarters is on a downtown Cambridge, Massachusetts street, right on a main intersection. If somebody wanted to blow up my building with a truck bomb, there's nothing I can do about it. Boom, I'm done, right? Everybody who I pitch that one to says, well, of course, we just live with that. We choose to be there. And that's not really likely to happen, but it's absolutely a hazard. And now I can talk about other hazards and choices that we make about how we operate our business. I have 250,000 servers in 136 countries. Guess what? At any given point, I have some of those countries that I'm worried are going to walk in and seize my servers. That's a hazard we have to live with to operate in the way that we choose to operate. And so for you, it's a thing to sort of think about. So there's a couple of lessons we've learned doing incident response for a long time that I always like to sort of leave people with and do as sort of as my wrap up, which is the first thing is to automate in advance as much as you can. And I include your queries. That if you have queries that you always run in an incident, that when you're doing an investigation, you go run this query. Does anybody else know about that query? Is that query running for you in an automated fashion? Do your operators get the access to the results of that query? Right? If you say, in fact, our operators have a very clear rule that if an alert has as a workflow tied to it, call an engineering team, they will not accept it. It's not allowed to be an operational alert if the very first thing they do is call an engineering team. The first thing they should do is the diagnostics the engineering team would do, and those should be automated, so in fact they get run and results are presented to them so they can at least start with a, what's happening? How might we fix this? Also important to understand that humans are not omnicompetent. The world in which you have one incident responder who can do all of the things an incident responder has to do pretty much doesn't exist. Those humans are really, really rare, and they're probably really valuable, and you don't want them doing all of the things like sending the emails about where we are. You also want to recognize that if you segregate these things, you can actually hand over jobs, because nobody should work on an incident for more than 8 hours at a stretch, and even that's pushing it. So have incident commanders or incident coordinators whose only job is to run the incident. They're not trying to fix anything. But when somebody says, hey, we need to have a side team to do this, they can program manage getting that side team in place, while you have other people whose job is to fix the problem. And other people whose job is to understand what impact you might be having to the rest of the business, and communicating with them, and writing messages. Customer communication in an incident is the thing most people overlook, and it should actually be often the first thing you should start doing, but you'd have somebody else start doing it. You should understand that some incidents are big and some are small. And how can you scale up? If I have an incident that is actually running across the whole planet, I'm probably going to have an incident team of 40 to 50 people who are working on that problem until we fix it. But if I have an incident that's a minor thing, it's maybe 2 or 3 people, the same process can work at both levels. But how do you know what scale level to use? How do you get to the right person, and how do you disrupt them? And that's for us the severity system. If I walk in and say, I've got a severity 1 incident, I need this engineer to work on this problem, that's what they're working on now. He's very excited that he got picked, or I need her to work on the problem, right? Find the right people to solve your incidents and understand if you have the authority to get their work involved. And finally, and this is probably the most important thing, is learn from your mistakes. You will fail in incidents. Everybody does. But when you fail, stop and relook at them. First of all, you were in an incident. That was a failure to begin with. But during the incident, what did you do wrong? What could you do better? What could you do faster? How could you get to humans more quickly? I probably spend more time on that aspect of incident management than on actually trying to solve the hazards themselves. Because if I can take an incident that takes 15 minutes to start up and get it down to 10 or to 8 or to 9, right, that starts to matter in terms of the impacts that I'm going to have across my customers and to the network as a whole. So I'd like to thank everybody for coming out today. So I gave you sort of a little brief view of how Akamai does our incident response and the planetary scale nature, and a little bit of how we use query and telemetry-based systems for that. Thank you very much.